is the first slide, which tells you where the eigenvalues and eigenvectors are used for. And that, like I said, this is the sort of intermediate stage. The actual applications will come from this diagonalization process. But first, let's just discuss that. That's where we need this. That's where we need our understanding of structure of matrix multiplication. So look at this. Here's my setting. Imagine I have a square matrix with scalars from some field f, and imagine we have performed spectral analysis of this matrix, something we've done a few times last week. So imagine we now know the eigenvalues of this matrix. So lambda 1, lambda 2, lambda n will be a sequence of e values. It's a nice abbreviation for the eigenvalue if you try to write this all the time. A sequence of e values of this matrix, and that's the corresponding sequence of e vectors for this matrix. Okay, so imagine we have done this spectral analysis and we have this information. Later on, I'm going to use the examples from last week where we have done so, and I'm going to show you how diagonalization works on those examples. But here I'll show you how it works on in a general setting. So here we go. My matrix, n times n, m, it may be different amount, no, m may be different from n, m eigenvalues and m eigenvectors. Now look at this. Relation between these two, by definition we should know now that when we call lambda a couple of objects, lambda and x, eigenvalue and eigenvector for a matrix, it means that they are connected by this relation. If you apply a to the matrix x, to the vector x1, it will be simply scaling of the vector x1 with the lambda 1 coefficient. If you apply vector to the if you apply matrix to the vector x2, it will be again simple scaling with a different coefficient, maybe different coefficient lambda 2, and that is true for every pair of lambda and x up to the mth pair. So here's my setting, and now look what I'm going to do now. I'm going to introduce a matrix which I'm going to call P, matrix P, which will consist of my eigenvectors as columns. So my P matrix is this matrix, the one which consists of the eigenvectors as columns. That's how big this matrix will be, because each individual x vector of size, well, this is a typo, obviously, because each of the vectors must be the same size as the matrix A. So let me just fix this typo. It's supposed to be n here. So each individual column of size n. So we have n rows, and altogether we have m columns. That's why we have m here. That's the first thing I'm going to consider. And now I'm going to consider the product, AP. Given my previous discussion, we know what happens of the how we multiply matrices from the structural point of view. If I multiply a matrix by some other matrix from the left-hand side, it is as good as multiplying each individual column here by the matrix A from the left-hand side. And that's what I'm going to do. I'm going to multiply each individual column here by the matrix A. Here's my product. First column, AX1. Second column, AX2. Last column, AXM. I just follow the observation from the slide, from the first slide today. But now I'm going to use this fact that lambdas and x's, they are just eigenvalue and eigenvector pairs. If I use that, I can continue the line like this. Each column becomes lambda 1 x1, lambda 2 x2, lambda m xm. Perfect. And at the final stage, I'm going to use the fact from my previous slide. Remember what happens? You remember how to achieve effect of scaling individual rows of the matrix with the coefficient? Because look what happened. I had my P matrix, and after I multiply my P with the A from the left-hand side, it turns out that every individual column of my P matrix got scaled by some coefficient. But we can achieve the same effect by other operation. We can achieve the same effect of individual scaling of columns by multiplying with the diagonal matrix from the right-hand side. That's something we discussed on the slide before. So I can achieve the same effect by multiplying my P matrix from the right-hand side by specifically crafted diagonal matrix. How do I craft this matrix D? I take these coefficients and put them on the diagonal. Here it is. So my D is my choice for the diagonal matrix, has the size of this diagonal matrix, and that's how it will be. This identity AP equal PG, this is what people call, I mean, it's an official name, but in our joint discussions, I'm going to call this semi-diagonalization of the matrix A. I'll explain the prefix semi-diagonalization. All right, so once again, you see, if you want to achieve semi-diagonalization with the matrix A, all you have to do, you have to find all of the eigenvalues, all of the eigenvectors, and then you have to build a P matrix, which consists of the eigenvectors as columns, and a D matrix, which is a diagonal one, and which has the eigenvalues on the diagonal. And the proof for this semi-diagonalization identity, that's the semi-diagonalization identity, AP equal PG. The proof basically is just structural understanding of matrix multiplication. Now, why is semi-diagonalization? What is the full diagonalization or just simple diagonalization? What are we missing to do the diagonalization? We're missing this. If I introduce an extra assumption, if it so happened that m equal n, if it so happened that the number of eigenvalues you were able to find is, or a number of eigenvectors, associated eigenvectors, is the same as the dimension of your matrix, if it so happened, and if extra so happened that the eigenvectors, this time you will have n of them, because m equal n, linearly independent, if it so happened, then what I can say in that case? In that case, I can say, that's the information we know from the first semester, that matrix P will be invertible. So there will be an inverse. In that case, P will be square matrix, right? If m equal n, P will be a square matrix, and not only that, it will be invertible because the columns are linearly independent. So it will be invertible, and what I can do then, I can multiply this identity. I can multiply this identity AP equal PG. I can multiply this identity by P inverse. Both left-hand side and right-hand side. If I do that, I will come up with this relation. P inverse times A times P equal exactly diagonal matrix D. Or I can multiply this identity by P inverse from the right-hand side, in which case I will come up with this relation, A equal P G P inverse. These two relations, either of them, because they're equivalent, you have to play with this P inverse factor in the right way. These two identities, this is what people call the diagonalization of, so it's a complete, so this was a semi-diagonalization, but this will be, I can kill the prefix semi now, it will be diagonalization of matrix A. So the difference between semi-diagonalization and diagonalization is that P must be square and invertible, for which you need linear independence of columns, the eigenvectors of matrix A. Diagonalization not always achievable. There will be one example here where it is not achievable, but the good news for you is that the spectral analysis, it's a relatively difficult topic, and you won't see much of it in the end of this course. So in your case, I suspect every example will be well diagonalizable, and your job will be to find that diagonalization. And when I say find that diagonalization, it means that you need to identify the P matrix and you need to identify the D matrix so that either this or this is true.